because it never stops, like Kevin said, right? Because if you go to f of 1, you end up at f of 0 and f of -1, and it just keeps getting smaller. So this will never finish. So how do you guys think we could change it so that it actually works? Yeah, so Kevin, what would you return if it's 1 or 0? Yeah, that's correct. So here's like the solution that actually works. Basically, instead of 0 or 1 here, we just have 1 or 2. But if x is 1 or 2, then you just return 1 because the definition of the Fibonacci sequence is the first two numbers of the 1. So you have to make sure you account for that here. But let's say you tried running this. Also, I'll just type in the main function that I didn't write. Okay, so let's say this is our complete code, but if you ran it, you might notice that this takes a really, really long time. Why do you think that is? Peyton?
Is that because it has a return 1?
Not exactly. Like, okay, let's go with a more simple example. So let's say you're trying to get f of 5. So then for 5, you need the values of 4 and 3. And then for 4, you need the values for 3 and 2. For 3, you need the values of 2 and 1. And then for this 3, you also need 2 and 1. But you have a problem here because you just calculated the value for 3 twice. So you're over calculating because you don't need to calculate it twice, right? Because you can just calculate all the values once and like store them somewhere instead of recalculating them every single time. Is that clear? Okay, and then even though for 5, this might not seem like such a big problem, when you get to 20, you calculate a ton of values like way more times than you need to calculate them. So it becomes a really big problem when the numbers get bigger. So we need a way to store our previous answers so that we can use them later. Does anyone have any questions? Ian, what does that mean? Oh, okay, so if you wanted to, I think I put this earlier, but a fully functional example would be something like this. Um, right, so this gives you, oh, and the headers of the text. So this is a complete working example. Try, if you want to run this for yourself, use this, like the entire thing. Okay, so for anyone that came late, the problem is you just want to find some term, like you just want to find any given term of the Fibonacci sequence. So like the 10th term or the 50th term, something like that. Okay, so if no one has any questions, I guess we can move on. So this is kind of what I just said, but when you try to get the value of f of 5, this is all the numbers that you're calling it with. So when you call f of 4, you need to know f of 4, I mean f of 5, you need to know f of 4 and f of 3. When you call f of 4, you need f of 3 and f of 2, and so on. So you can see that you calculated f of 2 3 times, f of 1 2 times, and then f of 3 2 times. So this is really redundant. So in order to just quicken the process, we can just store the values that we've already calculated so that we can reuse them later. So here's code that stores the values that you already calculated. So basically, a nifty trick in C++ is when you initialize a global array like this, that's not inside of main or any function, all the values are 0. So in this example, we can assume that if the value is 0, then we've never calculated it before because
What?
because all the values in the sequence are positive. So then if the stored value, oh, memo is just the array that we're using to store the values that we already calculated. So this just checks if there's already a value stored there, and if there is, you just return that value. And then we have our base case here. So if x is less than or equal to 2, we set memo to 1, and then we return that value. Otherwise, we set memo to this value, and then we just return it. So this way, we only calculate that for each number once. Did you guys have any questions about this? Oh, also, you can also message Ethan if you have questions. Okay, cool. So let's move on. Okay,
I'm sorry. I wish I was fast.
yeah, anyway.
Wait, what was that?
That was, nothing.
That I'm sorry. I wish I was something.
That
And
was, that
Well,
was,
I'm sorry, but what is it?
okay, guys, anyway.
Tell us.
So you might have noticed that since we're already using an array, you might have thought, well, you really don't need recursion for this, and you're right. You can simply like this that stores the values of the sequence, and then you store the first two values, which are 1, and then you loop through all the remaining values, and you just do this. So although this takes like the same amount of time as the previous solution, this one is much easier to, like, it's less lines, and always, if you don't have to use recursion, then don't use it, because it's like, 1, it's annoying to debug, and 2, not using recursion is always like slightly faster. Like not that much faster, but it's always slightly faster. So does anyone have questions about this solution? Okay, so let's move on to the next example problem. This is flood fill. So as you can see in this drawing, it's going through all the white squares that were connected to the center square and then making them orange. So this problem is a lot more complicated than the previous one. Also, if you guys want a link to the problem, I just put it in chat. Don't be afraid if like you don't like get the solution though. This is a pretty difficult problem. So flood fill is a pretty useful algorithm in competitive programming. Not just for the lower levels, but for the higher levels, it's also commonly used. And for some hints, you can define a function that processes a certain node, aka it changes the color of that node, and then it also goes to the nodes around it. So I'll give you guys a few minutes to think about it, and you can message me if you have any questions or ideas.
Who's sniffing?
Okay, I'll give you guys one more minute. Okay, so I guess I'll just go into the solution. Here's maybe a solution that you thought of. Basically, if the value at the position is equal to the source color, which is the color you want to change from, you're going to change it to the color that you want to change it to. And then after that, you're going to process all the adjacent locations. However, this doesn't work. And why do you think that is? Like, let's do a really simple example. So let's say you have a 2x2 array like this, and you start from here, and you want to change all the zeros to ones. So you could try running this in your head or something like that and see why it doesn't work. Okay, so does anyone have any ideas about why it doesn't work? Okay, I guess let's just try doing this. So here's the table. Here's the indexes. So this is 0, 1, 0, 1. And we start at the location 1, 0. So we have this is 0 and this is 1. Okay, so let's just run through this. Aij indeed equal to 0. So we change this color to 1. And then we go to 2, 0. Because here I is 1 and j is 0. But you see that 2, 0 is out of bounds because there's obviously no 2 here. So we don't do that. Then we come here. So this gives you 1, 1, and that's here. So you visit there. But when you call this, you get 1, 1, and this value becomes 1, and the source code is 0. So you just return from the function. So now you're back to 1, 0. Oops, let me draw that again. And you're moving on to the next direction. So let's say that this direction is up. So you come here. This actually is also 0, so you just change it to 1, and then you go to the other directions. Let's say you come here. This is also 0, so you change it to 1. And actually, this does work, but let's say you put all of this before this. Well, then that changes, right? Because let's say you had the same example. So you start from 0, you try all these directions, you go here, and then you return because this isn't 0. Yeah, Kevin, it is an infinite loop because then when you go up, you come here, and then you haven't changed this to 1 yet. So then if you come here, you visit all the directions, and then maybe you come back down. And then now you're back here again. And then you just repeat, and then you go back up, and then you come back down. So it is an infinite loop. So you have 2 options. You can either put this before this part, or you can check if you've already been to that location, and if you have, return. And now, well, actually, so instead of doing this check now, this won't work. So let's define an array called visited. And this array keeps track of whether you've already processed a certain location. So now what you can do is you replace this with visited. And then you set visited to true after that. So visited ij equals true. And then even if you move this stuff to here, it will still work. So do you guys get that? So when you're implementing flood fill, it's really important that you remember this, because otherwise it's very likely to just run infinitely. Oh, and also one thing that I failed to mention that's really important is, let's say you have the number of rows and columns. Of your function, you're going to want to check if I and j are actually in bounds. So let's say you have like a 2 by 2 array, and I and j are 5 and 5. And this is obviously not in bounds. So you're gonna have to check that, and if it's out of bounds, you also just have to return the value. So I guess, does anyone want to see like the C++ implementation? Okay, I guess. So here's the problem. Let's see. You're given the image, which is an array that's like this. You're given the starting location, the starting column, and the color that you want to change it to. So what you can do here is, let's initialize a variable. And then you're going to want to set the starting color to image SRSC. And then you're also gonna want to store the number of rows and columns. So and then the columns is also, columns. I'm sorry, what? So basically they represent the array here as a vector of vectors. So basically you can think of it as like, this is a vector. This is also a vector. And then you group them into another vector. So this kind of the array that looks like this. So the number of rows is just the size of the outer vector. It's just 2 elements in it. And the number of columns is the size of each individual vector. So I hope that's clear. And now we can define another function. We also want to keep another vector to store our final answer. And we're going to set this to the image for now. And then we're going to define another function that's DFS to do the flood fill. So DFS, I'll explain what DFS means later. So I can do this. And then a common trick for visiting all the directions is you define an array that gives you. So each of the directions can be represented by two numbers. One of them is how much you move to the right, and one of them is how far you go up. We can implement them here by just saying so basically the way you read this is these two match up. So let's say this is the direction in rows and this is the direction in columns. Then this means you don't move in the rows because it's 0, and you move 1 over in the columns. So this is equivalent to moving right. And then for -1, this is just equivalent to moving left. For this one, this is equivalent to moving down because you go down 1 row. And this is equivalent to going up. So that's a really easy way to encode all 4 directions. So now you can write a loop. And then just visit all of these. So this is like the skeleton for DFS. But you probably noticed that nothing is even calling this function right now. Here we can just call it from this origin and with color as a parameter. And then after that, we just return the answer. Hopefully this works. Oh, I have to sign up. Okay, let's run this and see what it says. Well, I said verify. Okay. Let's reload this. Okay, let's try running this. That's interesting. To add this. Ah, right. Make sure you don't forget your parameters. Let's see. Okay, this probably means that we just got into an infinite loop or something. Oh, I messed up. We can't reuse the variable I here. Oh, and by the way, since it's like, since class ran late, and if you have something to go, then if you have something to do, then you can like leave now, but otherwise it would be preferable if you stayed until 11:20. Okay, hopefully this works. Huh. Oh, I didn't take my own advice. That's to make sure that it's in bounds. Please work. What? Okay, does anyone see what's wrong here? Oh, okay. So I forgot that we need to add this to our bounce check. Also, this should be or, not and. There we go, first try. Okay, let's try submitting that. Runtime error. Huh. That's weird. What? Stack Overflow. Let's see. Okay, so basically what this means is there's an infinite recursion somewhere. Not really sure where, since this should work without the need of a visitor array, but let's just see.
Maybe like just check it from bottom to top. I mean, like that works.
What do you mean by that?
Like, I mean, this is fine. I mean, like, just read it and read it, I guess. I'm not sure.
Yeah,
This is fine. This one.
yeah, it's just somehow an infinite loop, and I'm not really sure why.
Or like sometimes, like for example, like other programming languages, sometimes it has something like there's a weird, like let's say there's a typo somewhere, or if there's like another error, then it changes. Like I don't know, but it kind of turns into a different error.
Oh, okay, give me a
Some
second.
people might like there might be something like a typo.
Oh, don't
Yeah.
worry. Basically, you just have to check. Okay, this is a really weird edge case, but if the source color is equal to the color that you're changing it to, then this will give you an infinite loop. Because, like, let's say you have the case of 0, 0, 0, 1. You change it to 0, then you go up, and you come back down. And since both the values are, this check really does not do anything. So it effectively just goes infinitely. So yeah, that was very trivial and easy. Let's move on. So Ian also asked, like, if we go back to the animation from earlier, you see that this only goes one direction at first, and then it goes the next direction, and then the next direction. But why doesn't it just spread from the middle? Like, well, that's because we're using the recursion. So let's like run a really simple example where it's just all zeros. And we're trying to convert it to 1. And if you notice from the implementation here, you visit all the directions in a certain order. So let's say that this order is something like right, left, up, down, or something. So then first you go right. Well, first it changes to 1. You go right, change it to 1. And then when you come here, you go to the right again, change this to 1. You try going right, doesn't work. Try going left, you already went there. And then you go up, 1. And then try going right, you try going left. And just going to the left, this is 1. So as you can see, when you do the DFS, it's not like you spread from the center. It's literally just you follow some arbitrary path until there's nothing left. So, and then for this example, this path is just kind of like this, right? Do you get that? Like basically what DFS does is it goes down a really long path until you hit like a wall or something, and then it goes back. Yeah. That's a good question, by the way. I'm also going to show you an alternative implementation that doesn't use recursion, that has different behavior. So this one utilizes a queue. And for those of you who don't know what a queue is, the data structure where you add numbers to the front. I mean, you add numbers to the back, and then you pop numbers from the front. So like you can add like 1, 2, you get the first value, and then remove the first value, and then add a 2, and then get the 2 at the front, and then delete it. So you can also use a queue for this problem. So let's say you have like 0, 0, 0, 0, 1, 0, 0, 1, 0. Let's just try to run this through. So let's say we start from the center, then we add 1, 1 to the queue. You get the value at the front of the queue, which at the moment is 1, 1. You delete it. And then if it's already changed, you just continue. And then otherwise, if it hasn't been changed yet, I forgot, you have to change it, obviously. And then you add all the directions to the queue. So here, you will change this to a 1, and then you add the right one to the queue. So this gives you 1, 2, 0, 1, and 2, 1, and 0, 1. Right? So, and then we just continue with the simulation. The next value that we get is 1, 2. This is 0, so we change it to 1. And then we add all these values to the queue. But the main observation that you should make here is that even though you visit this and you add like all its neighbors in, you're still going to come to this one first because it was added earlier. So what this effectively means is that you visit all the closer nodes first, well, all the closer points, and then you go to the further points. Another way to word this is all the points that are distance 1, you visit first, and then the points with distance 2, go to second, and then points with distance 3, and etc. So both of these applications have their own use. But in general, if you have a choice between these, you're usually going to pick this one because it's much easier to implement and it allows more like versatility and stuff. And they have like the same performance. So usually you pick this one, unless there's like a really good reason to pick this one. Okay, so let me check how much time we have left. Okay, we have 3 minutes left. I guess I'll just leave it up for any questions. And if you don't have questions, you can just leave. Or if you just want to talk about something else that's competitive programming related. Okay, so do you have any questions?